In this video, we will cover how to analyze and interpret solubility curves. We will begin by first defining what solubility is. So here in our slide, we have that the maximum amount of grams of solute that will be dissolved in 100 grams of solvent, usually water, at a given temperature. So really what this is telling us is that for solubility, or what we call solubility, is just how much of something that is going to be dissolved can actually be dissolved in 100 milliliters or grams of our solvent. And like I said, most of the time the solvent will be water. And here it analyzes the relationship between how much can be dissolved based on the temperature that is available for the solution. So before we begin actually looking at some of the curves, we are first going to determine how can we then classify some of these solutions. And most of us are very familiar with things that we know should have, for example, let's talk about sweet tea. We know what sweet tea is supposed to taste like, and we can also usually designate if something is not sweet enough or too sweet. So what we're really talking about here is concentration, and that is related to levels of saturation. The ideal, or what we would consider ideal, is what we usually call saturated. So that is the one I like to start here because that's what, in the perfect world, in the perfect conditions, at a certain temperature, you have added a particular amount of solute in your solvent. So you were able to dissolve exactly how much there needs to be in the solution. And that is, we call it saturated. Now, if we haven't added enough into our solution, so let's say that we're talking about sweet tea that is really not sweet at all. It just has a color, or it's very, very faint in color. Then we're talking about a solution that is unsaturated, meaning it has less than the optimal amount. And like I said, we usually designate something like that to be too diluted. And again, that would be for unsaturated, meaning it has less. You could still potentially add more and bring it to the saturated level that we want, the optimal amount. Now, what happens when we have added too much of our solute? In this case, that we're talking about sweet tea, we're talking about sugar or tea in a different scenario. Well, if we have added too much, then we have produced something that is a little bit too concentrated. It has too much of the solute in the solvent. So we call that super saturated. We have added way too much above what the optimal amount is. So in a different representation of that, or a different ideal here is, in this particular test tube, we're adding some solute, and it's being shown by little cubes. So in the first one on the left side, we have that it's an unsaturated solution. We can add and dissolve more of the solute. And usually, visually, how we can see that is here at the bottom, nothing is being collected. So we know, and also based on the color, that it doesn't really have that much solute in the solution itself. Now, when we talk about a saturated solution, remember, that is the optimal amount. That means that you can't really add more to it and expect for it to completely dissolve. So that usually we see that as you add more of your of your solute, it will directly go to the bottom and it will just collect. No matter how much you stir, no matter how much you shake your solution, nothing will happen. You will just add more and it just goes straight to the bottom and it collects there. So what is the difference visually when we talk about supersaturated? Well, crystals begin to form. And I'm not talking about just whatever you added collected at the bottom as we saw in the saturated solution. When you see that, you need to stop. Otherwise, you can potentially make your solution super saturated. And you will see that whatever you've been adding collects at the bottom and it forms crystals. So that is completely what we're looking for. So if you see crystals in the solution, automatically you know that it's been super saturated. You have added far above the saturated amount that you needed to have. So what does that look like in graphs? Okay, so before we begin to analyze them, we need to first see what is it that is shown on the graph itself. It's talking about the relationship between your solute and your solvent, specifically with temperature. So on the x-axis, So that's where we will have the temperature itself. And here, it doesn't matter if the temperature is in Celsius, Kelvin, doesn't really matter. We're just looking at the relationship of things. So its unit, it's not necessarily important. For the y-axis, we're talking about here about the solute. And like I said, we're usually talking about water, and the standard value for it will be 100 grams or 100 milliliters. So let's look at just a few examples so that we can see what is it that is going on, because we can see here that there's a lot of information. And also, hopefully some of you guys quickly notice that the gases and the solids, their lines overall have a different slope. And we know based on information that we've learned before that for solubility of gases and solids is going to be opposite in terms of temperature. So the higher the temperature for a solid, the more of it you can dissolve in your solute, in the water in this scenario. But for gases, it's completely opposite. The higher the temperature, the lower you will actually see its solubility being. So you will easily be able to tell, just based on the solubility curve like this one, if something is a gas or it's a solid when it's trying to be dissolved in your solution. So let's look at our first example. And the question is, what compound is the most soluble at 20 degrees Celsius? What this is asking us really is, if you have all of these solutions at 20 degrees Celsius, which of all of them can you add the most of to 100 grams milliliters of water? So we easily find 20 degrees Celsius. We compare all of our graphs and we find the one that basically intersects at 20 degrees Celsius at the highest value. So in this scenario, we can see that we have Ki, and you could potentially add up to about 145 of it. So our answer would be Ki, potassium iodide, and that would be the compound that is the most soluble, because you could add up to 145 grams of it to 100 grams of water. So let me go ahead and clear. Oh, it's not clearing. Okay, I guess not clearing. All right. So let's look at a different question. What is the solubility of NaNO3 at 40 degrees Celsius? So in this question, we're being asked specifically about a compound, sodium nitrate. So what we have is its locations right here. That's the line we're looking at, and it's asking us specifically at 40 degrees Celsius. So I'm going to go and find my 40 degrees Celsius, and identify where that line intersects with the particular curve that I'm looking at. And that intersects about right here. That's where we have it. So the question is asking us, what is the solubility? In other words, how much of sodium nitrate can you actually add to the 100 grams of water? And we would then compare that value here. And I do understand that the spacing and the information that's given on the solubility curve is not, it's not very detailed. So here you're going to have to make your best guess. I'm going to say is less than halfway through. So I'm going to call it about 100, let's go with 103 grams of NaNO3. And, you just have to make the best of the situation that you have available. So again, we just looked at the 40 degrees Celsius. We compared specifically to the curve that we're looking for. And then we looked at, okay, well, what does that on the range for grams of solute? Where does that fall? So let's look at one more question. Let me just first erase. Okay, and we're still using the same solubility curve. What kind of solution is made when 80 grams of KNO3 is dissolved at 30 degrees Celsius and then heated to 80 degrees Celsius? So first we have to figure out, okay, where is this particular compound we're looking for? Potassium nitrate, so that's right here. So we're talking about this very long, very steep curve. And it's asking us what kind of solution is made. So when they're asking you about the kind of solution or the classification or the type. It's asking us about, is this saturated, unsaturated, or supersaturated? So again, when you're being asked for kind, type, classification, we're talking about, okay, what kind of supersaturated or unsaturated, oh, it's not working, or just saturated regular. So first, let's identify what that is. So on our graph, we can see that we have at 80 degrees Celsius, our KNO3 is about, at 30 degrees Celsius and 80 grams. So we find that intersection, and that would fall around here. So we're talking about that it is above the line. And the line really truly represents your saturated solutions. The line represents exactly at that temperature what would be the ideal amount of your solute that should be in your graph, in your solution. Well, here what we're looking at is this little point on the table that is above the line. So that represents a solution that is super saturated. So anything above the line, super saturated. Now, this question is asking us what kind would be produced if we were to dissolve it, right? So right now we're super saturated, but then we increase the temperature to 80 degrees Celsius. So what if we were to go from 30 degrees to 80 degrees? So now we still haven't added any more. All we did was increase the temperature. So we're still at 80 grams, right? But now we moved to 80 degrees Celsius. So where that line intersects is about here. So if you notice, in comparison to the graph, to the line of potassium nitrate, this new period, this little dot on the curve, it is now underneath it. So now we have produced a solution that is unsaturated. So the answer to our question would be, what kind of solution was made when we went from 30 to 80 degrees without adding any more solute? And our answer would be, we produce an unsaturated solution. Alrighty, so we will continue more with solubility as we move forward.